Hi everyone, I'm Mahesh Dananjaya from University of Edinburgh, and the title of the talk is Lazy Release Persistency. In this talk, I will introduce our new persistency model called Release Persistency that strengthens the state-of-the-art language-level persistency model Acquire Release Persistency. And specifically, it makes it strong enough to enable recovery of log-free data structures on persistent memory. Then I'll talk about our microarchitectural mechanism called Lazy Release Persistency for efficiently enforcing RP. Emerging non-volatile memory devices like 3DX Point provides fast, fine-grained persistence. This potentially enables program recovery in the event of a crash without slowing down the program during normal execution. However, program recovery needs crash consistency. Upon a crash, what remains in the non-volatile memory should represent a consistent snapshot of the program execution. Let's understand crash consistency with an example. Consider a linked list with two nodes N1 and N2. Initially, the linked list is present both in the volatile cache and the non-volatile memory as shown. Now suppose we want to insert a new node A1 into the linked list. Accordingly, we first create the new node A1 and then we update its next pointer to point to N2 and then flip the base pointer. Now let's say that the base pointer is evicted from the cache and written back to the non-volatile memory. And at this very instant, there is a crash. Being volatile, the cache data is lost and recovery must happen from what remains in the non-volatile memory. But certainly, the linked list in the non-volatile memory is not in a consistent state. To enforce consistency, intuitively, we must control how data is written from the cache into the non-volatile memory. What primitives must be used for achieving crash consistency? There have been a number of language-level persistency primitives proposed for enabling crash consistency. But fundamentally, they can be classified into two types: those based on failure atomicity and those based on persist ordering. Each of these primitives are essentially trying to achieve a sweet spot between programmability and performance. Let's now look at atomicity in more details. With atomicity, the programmer encapsulates a bunch of updates within an atomic durable transaction. The system ensures that the group of updates persist together in an all or nothing fashion using some sort of logging. In the linked list example we saw earlier, the updates involved in creating the new node and modifying the pointers are all put inside the transaction. The advantage with atomicity is that it is relatively easy to use for the programmer. The disadvantage is that it requires some form of logging which is hard to implement efficiently. Now let's consider persist ordering. With persist ordering, the programmer carefully identifies points in the code where persist barriers need to be inserted. A persist barrier ensures that updates before the barrier must persist before updates after the barrier. In the linked list example, placing a barrier just before the base pointer is updated ensures crash consistency. This is because flipping the pointer essentially ensures the failure atomicity of the entire insertion process. The disadvantage with persist ordering is that it is hard for the programmer to identify the points at which these barriers need to be inserted. In some cases, it may be impossible to ensure crash consistency with only ordering primitives, in which case the compiler or runtime needs to employ the ordering primitive to ensure atomicity via logging. The advantage is performance. Especially in those applications that use only ordering, avoiding logging is clearly beneficial performance-wise. In particular, the state-of-the-art persistency model based on ordering, acquire-release persistency or ARP, shows how performance can be maximized with its efficient one-sided barrier semantics and the implementation. Let's understand ARP's one-sided barriers. Consider this multi-threaded code using flag synchronization where thread T1 releases the flag and thread 2 acquires the flag. Accordingly, the write to flag in thread T1 is marked release and read for a flag in T2 is marked acquire, which is standard practice in language level consistency models. Given this multi-threaded program with release and acquire labels, ARP ensures that the group of writes before the release are persisted before the group of writes after the acquire are persisted. If W1 refers to the group of writes before the release and W4 refers to the group of writes after the acquire, ARP ensures W1 to W4 order without enforcing W1 to W2 or W3 to W4 order. These one-sided persist barrier semantics are the key reason behind ARP's efficiency. Coming back to the atomicity versus ordering debate, our view is that while atomicity is indeed programmable, we believe languages should also support ordering. This is to enable crash consistency and recovery of the so-called lock-free data structures. What are lock-free data structures? These are codes that are similar to the linked list example we saw earlier. These data structures have the nice property of failure atomicity while only needing ordering. One way to understand these codes is by way of analogy to lock-free data structures, which are thread safe without having to require locks and critical sections. In a similar vein, lock-free data structure can be recovered without needing locks. We believe LFDs are an important use case for persistent memory, and there is much recent research on developing them. Unfortunately, we observe that the ordering semantics in ARP, acquire-release persistency, is not strong enough to enable recovery of lock-free data structures. To see why, let's consider the multi-threaded version of the same linked list example. Initially, there are two nodes in the linked list N1 and N2. Thread 1 now wants to insert a new node A1 between N1 and N2. Accordingly, it performs a bunch of writes, setting the phase of new node A1 and then setting its forward or next pointer. We refer to this group of writes as W1. Then the new node A1 is inserted into the linked list by performing an atomic compare and swap instruction, flipping the next pointer of N1 to make it point to A1. This compare and swap instruction is labeled a release because the compare and swap must take effect only after the previous writes have taken effect. What about the requirements for crash consistency? Interestingly, it is the same as visibility. That is, all of the writes in W1 must persist before the compare and swap itself persists. Why? Let's say that the compare and swap has persisted but not the new node itself. Clearly, the state of linked list is inconsistent in the non-volatile memory. Therefore, W1 must persist before the release. That is, the compare and swap write persists. Now let's say that thread 2 wants to insert a new node B2 between N1 and A1. Accordingly, it must first identify the appropriate point to insert by reading the link with the read marked acquire. Why acquire? Because the later updates to the list must not overtake this read. Subsequently, the new node B2 is created and inserted using compare swap instruction. We refer to the writes that follow the acquire, those that are used to create B2 and insert it as W2. What are the requirements for crash consistency? Clearly, writes involving B2 must persist only after the earlier writes involving A1 from thread 1 have persisted. Otherwise, the state of the linked list can be in inconsistent state, as shown. Therefore, W1 must persist before W4. We now show the instructions from the two threads T1 and T2. To summarize, we have established that W1 must persist before the release. Furthermore, W1 must persist before W4. Whereas, in this example, acquire was a simple read instruction. If it were another compare and swap instruction, we would also need the release to acquire persist ordering. Thus, in the general case, we need the following persist ordering for crash consistency. W1, the writes before the release, then the release followed by the writes that follow the acquire. The writes must persist in this order. Unfortunately, ARP is not strong enough in that it does not mandate all of these persist orderings. Thus, it is not strong enough to enable recovery of log-free data structures. Recall that ARP only mandates W1 to W4 ordering. It does not mandate W1 to release, release to acquire, or acquire to W4 ordering. In order to make log-free data structures recover correctly using ARP, two-sided full barriers must be inserted before the release and after the acquire. These two-sided full barriers, however, annul the performance benefit of ARP and its one-sided barriers. Therefore, we propose strengthening of ARP to a model called release persistency, in which persist ordering mirrors the consistency happens before ordering. This mirroring ensures the desired persist orderings, that is W1, then release write, followed by those writes after the acquire. It is worth noting that persist ordering mirroring the consistency ordering is probably sufficient for log-free data structures recoverability. Thus, release persistency has the potential performance advantage of one-sided barriers while also being strong enough for log-free data structure recoverability. In order to reap the performance benefits of release persistency, it must be efficiently implemented at the microarchitectural level. The challenge, though, is to enforce W1 to release to W4 order in a buffered manner. While it is tempting to block the release until all of the writes before it persists, that turns out to be suboptimal, as we will show later. The key observation here is that these requirements match those provided by a 30-year-old distributed shared memory protocol for enforcing release consistency lazily. Lazy release consistency works as follows. Upon release, the release write is simply written to the local cache. In particular, the writes before the release are not propagated to other processors at this point. On acquire, the matching release is identified and the dirty blocks in the releasing processor's cache is lazily propagated. Thus, data is propagated lazily to enforce release consistency. We adapt this idea to our context. On a release, we simply write to the local cache, and there is no need to persist writes before the release at this point. On an acquire, the matching release is identified via the coherence protocol, and the dirty blocks in the releasing processor are persisted. Thus, data is persisted lazily, that is, in a buffered manner, while enforcing release persistency. We evaluate our enforcement of release persistency using non-blocking data structures from the Synchro branch suite. We compare our implementation of release persistency and LRP against existing persist barrier implementations. The strict barrier represents the design where the release blocks until all of the writes before the release have persisted. The buffered barrier is an existing efficient two-sided barrier implementation. We perform our experiments in the prime simulation infrastructure. The graph shows the execution time for the different schemes normalized to volatile, that is, no persistency implementation. As we can see, LRP significantly improves upon the strict barrier, providing up to 71% reduction in execution time. In comparison with buffered two-sided barrier, LRP continues to show up to 44% improvement and average of 33% improvement. While both LRP and BB are buffered implementation, LRP is better because of its one-sided nature. Finally, it is worth noting that LRP is only 8% slower than the ideal no persistency comparison point. In summary, achieving crash consistency on non-volatile memory requires language-level persistency primitives. There is an ongoing debate on whether the primitives must use atomicity or ordering. Our view is that while atomicity is programmable and must be supported, ordering also should be supported. Why? Because an important class of log-free data structures can be recovered with only ordering and, crucially, without requiring any logging. We make the observation that the state-of-the-art ordering primitive, acquire-release persistency, is not strong enough for enabling the recovery of log-free data structures. We propose release persistency, a strengthening of ARP that enables recovery of log-free data structures while retaining the one-sided barrier in ARP. We then propose lazy release persistency and efficient microarchitectural implementation of release persistency. And our experiments show that LRP provides a 14 to 44% improvement over commonly used benchmarks. Please refer to our paper for the precise semantics of RP and microarchitectural details. Also, our simulator artifacts are available for download. Thank you.